Let's start with something simple. You're lying there right now, and gravity is pulling you into your mattress. You can feel it, that gentle, steady pressure holding you down. You don't think about it. You don't have to understand it. It just works. But here's the thing. If I asked you to explain gravity, really explain it, not just describe what it does, but tell me what it actually is, you'd probably pause. And that's okay. Because for most of human history, nobody could explain it either. They just knew things fell down. That's kind of where we're going to start tonight. With the stuff that seems obvious until you actually try to understand it. We're going to wander through some of the most confusing, most beautiful, most head-scratching scientific theories ever put together. Slowly, gently, one idea at a time. And if you drift off somewhere in the middle, that's perfectly fine. These ideas will still be here. They've been around for centuries, some of them. They can wait. So let's go back, way back, before laboratories, before universities, before anyone had even thought to write down an equation. Let's go to ancient Greece, maybe around 450 BC, and meet a man named Democritus. Now, Democritus didn't have a microscope. He didn't have any instruments at all, really. What he had was a knife and a thought experiment. He picked up a piece of cheese, or maybe it was bread. The sources aren't entirely clear on this, but let's say cheese, and he started cutting it in half. Then he cut one of those halves in half, then again, and again. And he asked himself a question that sounds almost childlike, but turns out to be one of the deepest questions in all of science. Can you keep cutting forever? Think about that for a second. If you keep dividing something, do you eventually reach a piece so small it can't be divided anymore? Democritus decided yes, there had to be a smallest piece, a fundamental unit of matter, something you couldn't cut any further. He called it atomos, uncuttable. And just like that, sitting there with his cheese and his knife, he'd stumbled onto one of the most important ideas in the history of science. Not because he was right about the details. He wasn't, not really. But because he'd asked the right question. Is there a bottom to reality? Is there a smallest thing? Now here's what's kind of tragic about Democritus. His idea didn't win. Not in his lifetime, not for a long time after, because he was up against a much more famous philosopher, Aristotle. And Aristotle said no, matter is continuous. You can keep dividing forever. There is no smallest piece. Matter is made of 4 elements: earth, water, air, and fire. And that's the end of it. And because Aristotle was Aristotle, because he was the most influential thinker in the Western world for nearly 2,000 years, his view dominated. Democritus's atoms were mostly forgotten, shelved, gathering dust in the margins of history. And that's worth sitting with for a moment, because it tells you something important about how science actually works. It's not this clean, straight line from ignorance to knowledge. It's messy. Good ideas get buried. Wrong ideas get enshrined. Politics, personality, prestige. They all play a role. The truth doesn't always win just because it's true. Sometimes it has to wait. So atoms waited. They waited through the Roman Empire, through the Middle Ages, through centuries of alchemy and superstition. They waited until the late 1700s, when a quiet, colorblind schoolteacher in Manchester, England, started doing something nobody had done carefully enough before. His name was John Dalton, and what he did was weigh things. Dalton was methodical, almost obsessively so. He measured how different substances combined with each other, how much oxygen reacted with how much hydrogen, how much carbon combined with how much oxygen, and he noticed something. The ratios were always simple whole numbers, not 1.7 to 3.4, not some messy decimal, but clean ratios like 1 to 1, or 1 to 2, or 2 to 3. And the simplest explanation for that, the explanation that made everything click, was that matter came in discrete little packets. Atoms. Democritus had been right all along. You couldn't keep cutting forever. There really was a smallest piece. Dalton published his atomic theory in 1808, and it was beautifully simple. Each element is made of identical atoms. Atoms of different elements have different weights. Chemical reactions are just atoms rearranging themselves into new combinations. That's it. Clean, elegant, powerful. And for about 100 years, it worked brilliantly. Chemists used it to predict reactions, to discover new elements, to build the periodic table. The atom was this solid, indivisible little ball, like a tiny billiard ball, and everything in the universe was made of them. But here's the thing about science. Every answer opens up new questions, and the question that started gnawing at people toward the end of the 1800s was this: if atoms are the smallest things, why do they behave so differently from each other? Why is gold gold and oxygen oxygen? What makes one atom different from another? If they're really just featureless little balls, what gives them their individual personalities? The first crack in the billiard ball model came in 1897, and it came from a man working in a basement laboratory at Cambridge University. J.J. Thomson was experimenting with cathode rays, those eerie glowing beams you get when you run electricity through a glass tube with most of the air pumped out. You've seen the descendants of those tubes, by the way. Old television sets, the big boxy ones. Those were cathode ray tubes. Same basic idea. Thomson did something clever. He put magnets and electric plates near the beam and watched it bend. And from how much it bent, he could calculate the mass of whatever was carrying the charge. And what he found was startling. These particles were tiny, absurdly tiny, about 2,000 times lighter than the lightest atom, hydrogen, which meant they couldn't be atoms. They had to be pieces of atoms, parts of something that was supposed to be indivisible. Thomson had discovered the electron, and in doing so, he'd blown a hole in Dalton's beautiful, simple model. Atoms weren't solid little balls. They had structure. They had pieces inside them. The uncuttable had been cut. Now Thomson was a careful man, and he tried to make sense of what he'd found. He proposed a model, sometimes called the plum pudding model, which is a very British name for a scientific theory. Imagine a ball of positively charged stuff, like a blob of pudding, with tiny negatively charged electrons scattered through it like raisins. The positive and negative charges balanced out, so the atom as a whole was neutral. It was a reasonable guess. It made sense with what they knew at the time. But it was wrong. And the man who proved it wrong was one of Thomson's own former students, a big, loud New Zealander named Ernest Rutherford, working at the University of Manchester in 1909. Rutherford's experiment is one of those stories that's so perfect it almost sounds made up. He had two assistants, Hans Geiger and Ernest Marsden, and he told them to fire tiny, fast-moving particles, alpha particles, which are basically the nuclei of helium atoms, at a thin sheet of gold foil, really thin, just a few hundred atoms thick. If Thomson's plum pudding model was right, the alpha particles should have passed straight through with barely any deflection, like shooting a bullet through a cloud of cotton candy. The positive charge was supposed to be spread out evenly, So there was nothing dense enough to really deflect anything, and most of the alpha particles did pass straight through, but some of them bounced back. Not just deflected a little. Some of them came almost straight back toward the source. Rutherford later said it was as if you'd fired a 15-inch artillery shell at a piece of tissue paper and it came back and hit you. He was genuinely shocked. What that meant, and this is where it gets really beautiful, was that almost all the mass of the atom and all of its positive charge was concentrated in an incredibly tiny, incredibly dense point at the center, the nucleus. And the rest of the atom was mostly empty space, with those tiny electrons orbiting way out at the edges. If you scaled an atom up to the size of a football stadium, the nucleus would be about the size of a marble sitting on the 50-yard line. Everything else, the seats, the field, the parking lot, would be empty. You are, when you get right down to it, almost entirely made of nothing. Think about what that means. Your hand, resting there on the blanket, it feels solid. It feels like a thing. But at the atomic level, it's overwhelmingly empty space. The reason it feels solid, the reason your hand doesn't pass through the mattress, has nothing to do with physical objects bumping into each other. It's about forces, electromagnetic forces between electrons, repelling each other, creating the illusion of solidity. But we'll come back to forces later. That's a whole other thread to pull on. For now, let's stay with Rutherford and his nucleus, because his discovery created a new problem. A big one. According to everything physicists knew about electricity and magnetism, the classical laws laid down by James Clerk Maxwell just a few decades earlier, Rutherford's atom shouldn't work. It shouldn't even exist. Here's why. An electron orbiting a nucleus is a charged particle moving in a circle. And Maxwell's equations are very clear about what happens when a charged particle accelerates. And moving in a circle counts as acceleration, even if your speed isn't changing, because your direction is always changing. A charged particle that's accelerating radiates energy. It gives off electromagnetic waves, light, and as it loses energy, it should spiral inward, faster and faster, radiating more and more frantically until it crashes into the nucleus. The math said this should happen in about 100 trillionth of a second. Every atom in the universe should have collapsed almost instantly. But atoms don't collapse. They're stable. They've been stable for billions of years. So something was deeply, fundamentally wrong with the classical picture. Either Maxwell's equations were wrong, and they'd been tested thousands of times and worked perfectly for everything else, or something very strange was happening inside atoms, something that didn't follow the old rules. And this is the moment where physics starts to get genuinely weird. Because the answer to this puzzle didn't come from tweaking the existing theory or finding a small correction. It came from a completely new way of thinking about reality. A way of thinking so strange, so counterintuitive, that the people who invented it spent the rest of their lives arguing about what it actually meant. The first hint had actually come a few years before Rutherford's experiment, from a very different problem. In 1900, a German physicist named Max Planck was trying to solve what seemed like a fairly technical puzzle about how hot objects glow. You know how a piece of metal changes color as it heats up. First it glows a dull red, then orange, then yellow, then white hot. Physicists had been trying to write down an equation that predicted exactly how much light a hot object gives off at each color, each wavelength. And they couldn't do it. The classical theory gave answers that worked at some wavelengths but went completely haywire at others. It predicted that a hot object should radiate infinite energy at short wavelengths, which was obviously nonsense. They called it the ultraviolet catastrophe, which is a wonderfully dramatic name for a math problem. Planck found a fix. But to make his equation work, he had to assume something that made no physical sense to him at the time. He had to assume that energy wasn't continuous, that it came in tiny, discrete packets. He called them quanta, from the Latin word for how much. Energy could only be emitted or absorbed in these specific little chunks, not in any arbitrary amount. It was like saying you could walk up a staircase one step at a time, but you could never stand between the steps. Planck himself didn't really believe this was how nature actually worked. He thought it was a mathematical trick, a clever shortcut that happened to give the right answer. He spent years trying to find a way to get the same result without the quanta. He never could. And meanwhile, a young patent clerk in Bern, Switzerland, was about to take Planck's reluctant idea and run with it in a direction that nobody expected, least of all Planck. Albert Einstein, in 1905, was 26 years old. He wasn't a professor. He wasn't at a prestigious university. He was working at the Swiss patent office in Bern, examining other people's inventions, and doing physics in his spare time. And in that single year, 1905, which physicists sometimes call his miracle year, he published 4 papers that each, on their own, would have been enough to make a career. But the one that matters for us right now is the one about light. See, there was another puzzle that classical physics couldn't solve, and it had to do with what happens when you shine light on a piece of metal. It's called the photoelectric effect. If you take ultraviolet light and aim it at a metal surface, electrons pop off. That part wasn't surprising. Light carries energy. Energy knocks electrons loose, fine. But the details were all wrong. Classical physics predicted that if you used brighter light, the electrons should come off with more energy. They didn't. Brighter light knocked off more electrons, but each individual electron had the same energy as before. What actually changed the energy of the electrons was the color of the light, its frequency. Higher frequency light, like ultraviolet, produced higher energy electrons. Lower frequency light, no matter how blindingly bright you made it, sometimes couldn't knock off any electrons at all. There was a sharp cutoff. Below a certain frequency, nothing happened. Above it, electrons flew off immediately, even if the light was incredibly dim. This made absolutely no sense if light was a wave. A wave's energy depends on its amplitude, how big the wave is, how bright the light is. Frequency shouldn't matter the way it did. Einstein looked at this problem, looked at what Planck had done with his quanta, and made a bold leap. He said, "What if light itself actually comes in little packets of energy? Not just that energy is emitted in chunks, the way Planck cautiously suggested, but that light literally travels as discrete particles, each one carrying an energy that depends on its frequency." He called these particles light quanta. We call them photons now, though that word didn't come along until the 1920s, and suddenly the photoelectric effect made perfect sense. Each photon carries a specific amount of energy determined by its frequency. When a photon hits an electron in the metal, it's a one-on-one interaction. One photon, one electron. If the photon has enough energy, the electron escapes. If it doesn't, nothing happens, no matter how many low-energy photons you throw at the surface. Brighter light just means more photons, so more electrons get knocked loose, but each electron still receives energy from only one photon. It's like the difference between being hit by one fast baseball versus being pelted with 1,000 ping-pong balls. The ping-pong balls might be annoying, but they won't knock you off your feet the way that single baseball will. Here's what's really striking about this. Einstein essentially said that light is a particle, but we already knew from over a century of experiments, from Thomas Young's famous double-slit experiment in 1801, from the entire framework of Maxwell's equations, that light is a wave. It diffracts, it interferes, it does all the things waves do. And now Einstein was saying it's also a particle, both, at the same time. This wasn't a contradiction that got resolved quickly. It haunted physics for the next 2 decades. And honestly, in a deep sense, it's never been fully resolved in a way that feels comfortable to human intuition. We've just gotten better at accepting it. But let's not rush ahead. Let's stay with the early 1900s for a moment, because things were getting wonderfully strange, and there were several threads all tangling together at once. You had Rutherford's atom with its tiny nucleus and orbiting electrons, the atom that shouldn't exist because classical physics said those electrons should spiral inward and crash. You had Planck's quanta and Einstein's photons, suggesting that energy and light come in discrete packets. And in 1913, a young Danish physicist named Niels Bohr took these threads and wove them into something new. Bohr was working in Rutherford's lab in Manchester, and he was bothered by the same problem everyone was bothered by. Why don't atoms collapse? His solution was audacious and, by classical standards, completely unjustified. He simply declared that electrons can only orbit the nucleus at certain specific distances. Not any orbit they want. Only certain allowed orbits, like the rungs of a ladder. An electron can be on this rung or that rung, but never in between. And when an electron is in one of these allowed orbits, it just doesn't radiate energy. It's stable. Period. Don't ask why. It just is. Now, that sounds like cheating, right? Just declaring that the rules don't apply. But here's the thing. Bohr tied his allowed orbits to Planck's constant, that same tiny number from Planck's original quantum hypothesis. The angular momentum of the electron in each orbit had to be a whole number multiple of Planck's constant divided by 2 pi. And from that single assumption, Bohr could calculate the exact wavelengths of light that hydrogen atoms emit. He could predict the hydrogen spectrum, those specific colors of light that hydrogen gives off when you heat it up or run electricity through it. And his predictions matched the experimental measurements to extraordinary precision. Not roughly, not approximately, exactly. Think about what that means. For decades, people had been cataloging the precise wavelengths of light emitted by different elements. They had these beautiful, mysterious patterns of spectral lines, each element with its own unique fingerprint of colors. Hydrogen's pattern had been described by a Swiss schoolteacher named Johann Balmer in 1885, who found a simple mathematical formula that fit the visible lines. But nobody knew why that formula worked. It was just a pattern with no explanation. And now Bohr came along and derived Balmer's formula from first principles, from this strange new idea about quantized orbits. The formula wasn't just a lucky guess anymore. It was a consequence of the quantum structure of the atom. This was enormously exciting, but also deeply unsettling. Bohr's model worked beautifully for hydrogen, which has just 1 electron. But it started to break down for heavier atoms. It couldn't properly handle helium, which has 2 electrons. The orbits got too complicated, the interactions between electrons were too messy. And philosophically, the model was troubling because it was a strange hybrid. It used classical physics for some things, and then just overrode classical physics with quantum rules whenever it was convenient. There was no deeper theory explaining why the quantum rules existed. They were imposed by hand, like patches on a leaky boat. Still, Bohr's model established something crucial. It showed that the quantum, this idea of discreteness, of specific allowed values rather than a continuous range, wasn't just about light. It was about matter itself. The structure of atoms was quantized. And if atoms are quantized, then in some sense, everything is quantized, because everything is made of atoms. Now, while all this was happening in the world of atoms and light, there was another scientific revolution unfolding in parallel, and I want to take a little detour into it, because it connects to everything we'll talk about later. This is Einstein again, but a different side of Einstein. In 1905, the same year he explained the photoelectric effect, he also published his special theory of relativity. And in 1915, he completed his general theory of relativity. These are the theories that deal with space, time, gravity, and the speed of light, and they're often presented as completely separate from quantum mechanics. But they grew from the same soil of dissatisfaction with classical physics, and they're entangled with the quantum story in ways that still cause headaches for physicists today. Special relativity starts from two simple postulates. First, the laws of physics are the same for everyone moving at a constant speed. There's no experiment you can do inside a sealed room that tells you whether you're moving or standing still, as long as you're not accelerating. Second, and this is the strange one, the speed of light in a vacuum is the same for everyone, no matter how fast they're moving. That sounds innocuous, but think about it. If you're on a train going 60 miles an hour and you throw a ball forward at 20 miles an hour, someone standing on the platform sees the ball going 80. Speeds add up. But light doesn't work that way. If you're on a spaceship going half the speed of light and you turn on a flashlight, the light doesn't go 1.5 times the speed of light from the platform's perspective. It goes exactly the speed of light, always, for everyone. To make that work mathematically, Einstein had to accept that space and time themselves are flexible. They stretch and compress depending on how fast you're moving relative to someone else. Time passes more slowly for someone moving fast. That's time dilation. Lengths contract in the direction of motion. That's length contraction. And mass and energy turn out to be two forms of the same thing, related by probably the most famous equation in all of science. E equals mc squared. Energy equals mass times the speed of light squared. And because the speed of light is enormous, about 300 million meters per second, even a tiny amount of mass corresponds to a staggering amount of energy. That's why nuclear reactions are so powerful. When a uranium atom splits, a tiny fraction of its mass converts to energy, and that tiny fraction, multiplied by the speed of light squared, is enough to level a city. Now, special relativity deals with constant speeds, with things moving in straight lines at steady velocities. But what about gravity? What about acceleration? That's where general relativity comes in, and it's one of the most beautiful ideas in all of physics. Einstein spent 10 years working on it, from 1905 to 1915, and it nearly broke him. The math was ferociously difficult. He had to learn an entirely new branch of mathematics called tensor calculus, and there were times when he was stuck for months, going down wrong paths, publishing equations that turned out to be incorrect, and having to backtrack. But the core insight is breathtaking in its elegance. Einstein realized that gravity isn't a force pulling objects toward each other the way Newton described it. Instead, Gravity is the curvature of space-time itself. Massive objects like stars and planets bend the fabric of space and time around them, and other objects follow curved paths through this warped space-time. The Earth doesn't orbit the Sun because some invisible rope is pulling it. It orbits because the Sun's mass has curved space-time in its vicinity, and the Earth is following the straightest possible path through that curved geometry. It's like placing a bowling ball on a stretched rubber sheet and then rolling a marble nearby. The marble curves toward the bowling ball, not because the bowling ball is pulling it, but because the sheet is deformed. This was confirmed spectacularly in 1919, when the British astronomer Arthur Eddington led an expedition to observe a total solar eclipse off the west coast of Africa. During the eclipse, when the sun's glare was blocked by the moon, Eddington photographed stars that appeared near the edge of the sun. Their positions were slightly shifted compared to where they normally appeared in the night sky. The sun's gravity was bending the starlight, curving it as it passed close to the sun, exactly as Einstein's equations predicted. When the results were announced, Einstein became the most famous scientist in the world overnight. Headlines everywhere. The man who bent light. And here's where things start to get really interesting, because now you have two revolutionary frameworks sitting side by side. You have quantum mechanics, which describes the very small, atoms, electrons, photons, with its strange rules about discreteness and probability. And you have general relativity, which describes the very large, stars, galaxies, the expansion of the universe, with its elegant geometry of curved space-time. Both theories are spectacularly successful in their own domains. Both have been tested to extraordinary precision. And they are, as far as anyone can tell, fundamentally incompatible with each other. That incompatibility is one of the deepest unsolved problems in all of physics, and we'll come back to it. But first, let's return to the quantum side of things, because in the 1920s, the patchwork of quantum ideas, Planck's quanta, Einstein's photons, Bohr's orbits, was about to be replaced by something far more powerful and far more strange. A full mathematical theory of quantum mechanics was about to be born, and it came from an unlikely direction. A French prince, of all people, was about to propose an idea so radical that his doctoral thesis committee didn't know whether it was brilliant or insane, and they had to send it to Einstein to find out. The prince's name was Louis de Broglie, and his idea was this: if light, which everyone had always treated as a wave, could behave like a particle, then maybe particles, like electrons, could behave like waves. That's it. That's the whole idea, and it sounds almost too simple when you say it out loud. But think about what he was really suggesting. De Broglie was saying that an electron, this tiny, hard little speck of matter that you can weigh, that you can deflect with a magnet, that leaves tracks in cloud chambers, has a wavelength. It ripples, it undulates. It has all the properties that you'd normally associate with something like sound or light or water waves. And he even wrote down the formula. The wavelength of any particle, de Broglie said, is equal to Planck's constant divided by the particle's momentum. So the heavier or faster something is, the shorter its wavelength. For something like a baseball, the wavelength is so absurdly tiny, trillions of times smaller than an atom, that you'd never, ever notice any wave behavior. But for something as light as an electron, the wavelength is comparable to the spacing between atoms in a crystal, and that means, in principle, you could actually detect it. Now, here's what makes this story so delightful. De Broglie submitted this idea as his doctoral thesis at the University of Paris in 1924. His thesis advisor, Paul Langevin, was a respected physicist, but even he wasn't sure what to make of it. The idea was so unusual, so out of left field, that Langevin reportedly said something like, "I don't know whether this is brilliant or crazy." So he did something unusual. He sent a copy of the thesis to Albert Einstein and asked for his opinion. And Einstein, who by this point was the undisputed authority on pretty much everything in physics, read it and replied that de Broglie had lifted a corner of the great veil. He thought it was brilliant. He thought it was right. And that endorsement was enough. De Broglie got his doctorate. But here's the thing. It was still just a hypothesis, a beautiful, elegant hypothesis with a neat formula, but no experimental proof. That came 3 years later, in 1927, when 2 separate experiments confirmed that electrons really do behave like waves. Clinton Davison and Lester Germer, working at Bell Labs in New York, fired electrons at a nickel crystal and found that the electrons scattered in a pattern that made no sense if electrons were just particles, but made perfect sense if they were waves diffracting off the regular rows of atoms in the crystal, exactly the way X-rays diffract off crystals. Around the same time, George Paget Thomson, and yes, that's J.J. Thomson's son, did a similar experiment in Scotland, firing electrons through thin metal foils and getting the same kind of diffraction rings you'd expect from waves. So the father discovered the electron as a particle, and the son helped prove it was also a wave. Both of them won Nobel Prizes for it. Physics has a sense of humor sometimes. So now you're in this extraordinary situation. Light is both a wave and a particle. Electrons are both a particle and a wave. And the natural question is, well, what does that even mean? What is an electron really? Is it a tiny ball that sometimes pretends to be a wave? Is it a wave that sometimes pretends to be a ball? And the honest answer, the answer that quantum mechanics eventually settled on, is that it's neither, or both. It depends on how you look at it, and that's not a cop-out. That's actually the deep truth that the theory reveals. But we're getting ahead of ourselves a little, because before anyone could fully grapple with that question, the mathematical machinery of quantum mechanics had to be built. And it was built, remarkably, by 2 very different people working almost simultaneously and arriving at what appeared to be completely different theories, until someone proved they were actually the same theory wearing different clothes. The first was Werner Heisenberg, a young German physicist who was barely 23 years old in 1925. Heisenberg had studied under Niels Bohr in Copenhagen and under Max Born in Göttingen, and he was deeply frustrated by the state of atomic physics. Bohr's model worked for hydrogen, but failed for everything else. There were all these ad hoc rules, quantum numbers, selection rules, half-integer spins, that had been bolted on to try to make the theory work for more complex atoms, and the whole thing felt like a house of cards. Heisenberg decided to take a radical approach. He said, "Look, we've been trying to picture what's happening inside the atom, electrons orbiting like little planets, and it's not working. So what if we stop trying to picture it? What if we build a theory based only on things we can actually observe, the frequencies and intensities of the light that atoms emit, and forget about trying to describe orbits that nobody has ever seen?" And here's a lovely detail about how this breakthrough happened. In the early summer of 1925, Heisenberg was suffering from terrible hay fever. His face was so swollen he could barely see. So he left Göttingen and went to Helgoland, a tiny, windswept island in the North Sea where there was almost no pollen. And there, alone on this barren rock in the middle of the ocean, working through the nights, he developed what became the first complete formulation of quantum mechanics. He replaced the idea of electron orbits with arrays of numbers, tables of quantities that described the transitions between energy states. When he multiplied these arrays together, he noticed something strange. The order of multiplication mattered. A times b did not equal b times a. If you've ever done basic algebra, you know that for ordinary numbers, multiplication always commutes. 3 times 5 is the same as 5 times 3. But Heisenberg's quantities didn't obey that rule. He wasn't sure what to make of this. And when he showed his work to Max Born, Born immediately recognized what Heisenberg had stumbled onto. These arrays were matrices, mathematical objects that had been studied by mathematicians for decades, but had never really been used in physics. Born, along with his student Pascual Jordan, helped Heisenberg formalize the theory into what became known as matrix mechanics. It was abstract, it was powerful, and it worked. It could predict the spectral lines of atoms with remarkable accuracy, but it was also deeply unintuitive. There was nothing in it you could visualize. No orbits, no trajectories, no mental picture of what an electron was doing. Just matrices and algebra. And then, almost immediately afterward, along came Erwin Schrödinger, with what seemed like a completely different approach. Schrödinger was Austrian, a bit older than Heisenberg, and temperamentally very different. Where Heisenberg was willing to abandon visualization entirely, Schrödinger wanted a theory you could picture. He was inspired directly by de Broglie's idea of matter waves, and he asked, if an electron is a wave, then there should be a wave equation that describes it, just like there are wave equations for sound or light or vibrating strings. And in late 1925 and early 1926, during a remarkably productive period at a villa in the Swiss Alps, and reportedly in the company of a woman who was not his wife, though history has never quite pinned down who she was, Schrödinger derived his famous equation. The Schrödinger equation is, in a sense, the Newton's second law of quantum mechanics. Newton's law tells you how a particle moves when you apply a force. Schrödinger's equation tells you how a quantum wave function evolves over time. And when Schrödinger applied it to the hydrogen atom, out popped all of Bohr's energy levels, not as ad hoc assumptions, but as natural mathematical consequences of the equation, the way specific musical notes emerge naturally from a vibrating guitar string. The allowed energy levels corresponded to standing wave patterns, just like the harmonics of a string. It was beautiful. It was visual. You could picture the electron as a wave wrapped around the nucleus, vibrating in specific patterns. Physicists were thrilled, or at least some of them were, because now there were two theories of quantum mechanics, and they looked completely different. Heisenberg's matrix mechanics was all abstract algebra, no pictures. Schrödinger's wave mechanics was all smooth, continuous waves, very picturable. They gave the same answers, but they seemed to be saying completely different things about what was really going on. Heisenberg reportedly said that Schrödinger's approach made him feel physically ill. Schrödinger said he was repelled by Heisenberg's matrices. It was a genuine intellectual rivalry, not just a polite disagreement. And then, in 1926, Schrödinger himself proved that the two theories were mathematically equivalent. They were the same theory, expressed in different mathematical languages. It was like discovering that two people who seemed to be telling completely different stories were actually describing the same events, one in French, one in German. This was a profound result, because it meant that the underlying physics didn't depend on which mathematical language you chose. The truth was deeper than either formulation. But here's where things got really unsettling. And this is the part that still keeps physicists up at night. Schrödinger's equation describes a wave function. But what is the wave function? What is it a wave of? Schrödinger himself initially thought it described a real physical wave, that the electron was literally smeared out in space, a cloud of charge spread around the nucleus. But Max Born proposed a different interpretation, one that Schrödinger hated, but that turned out to be the one that stuck. Born said the wave function doesn't describe the electron itself. It describes the probability of finding the electron in a particular place. The square of the wave function at any point gives you the likelihood that if you look there, that's where the electron will be. Think about what that means. Before you measure it, the electron doesn't have a definite position. It's not that we don't know where it is. It genuinely doesn't have a specific location. It exists in a kind of cloud of possibilities, and only when you make a measurement does it snap into a definite position. This is not a limitation of our instruments. It's not that we need a better microscope. It's a fundamental feature of reality at the quantum scale. And this idea that nature is inherently probabilistic, that the best you can ever do is calculate probabilities, was deeply disturbing to many physicists, including, famously, Einstein, who never fully accepted it. God does not play dice, he reportedly said, to which Niels Bohr supposedly replied, "Stop telling God what to do." And this probabilistic interpretation connects directly to another idea that Heisenberg published in 1927, one that has become one of the most famous principles in all of science, though it's also one of the most misunderstood. He called it the uncertainty principle, and what it says is that there are certain pairs of properties, position and momentum being the most famous pair, that you cannot know both of with perfect precision at the same time. And here's the crucial thing. The part that most people get wrong. This is not about your measurement disturbing the particle. It's not that you bump the electron with your photon and knock it off course. That was actually the way Heisenberg himself first explained it, using a thought experiment he called the gamma-ray microscope. And it's a reasonable intuition, but it's misleading. The uncertainty principle is deeper than that. It's saying that a particle literally cannot have both a perfectly defined position and a perfectly defined momentum simultaneously. It's not a statement about what you can know. It's a statement about what can be. And if you think about it in terms of waves, it actually makes a kind of intuitive sense. Picture a wave that has a very precise frequency, a pure musical tone, a single note humming along forever. That wave is spread out everywhere. It doesn't have a location. Now picture a wave that's very localized, a sharp pulse, a spike. You can point to exactly where it is, but it doesn't really have a well-defined frequency anymore, because it's not a smooth repeating wave, it's a burst. So the more precisely you pin down one quality, the more the other one smears out. That's the trade-off, baked into the mathematics of waves themselves. And since quantum mechanics tells us that particles are described by wave functions, this trade-off comes along for the ride. Position and momentum are what physicists call conjugate variables, and there's a hard mathematical limit. Heisenberg showed that the uncertainty in position multiplied by the uncertainty in momentum can never be less than a tiny constant. Planck's constant divided by 4pi. For anything human-sized, this limit is so absurdly small that it's irrelevant. You will never notice it when you throw a baseball. But for an electron, it's everything. Now, 1927 was a remarkable year for quantum mechanics, not just because of the uncertainty principle. That October, some of the greatest physicists alive gathered at the 5th Solvay conference in Brussels, and the photograph from that meeting is one of the most famous images in the history of science. 29 physicists, 17 of whom were or would become Nobel laureates. Einstein is there, front and center. Marie Curie is there. Bohr, Heisenberg, Schrödinger, Born, Dirac, Pauli, de Broglie, Lorentz. It's almost absurd how much intellectual firepower was in that one room. And the topic of the conference was the newly minted quantum theory, What did it mean? How should it be interpreted? And this is where the famous debates between Einstein and Bohr really caught fire. By this point, Bohr and Heisenberg and their colleagues in Copenhagen had assembled what became known as the Copenhagen interpretation of quantum mechanics. And the core ideas go something like this. A quantum system exists in a superposition of states until it's measured. The wave function gives you probabilities, not certainties. When you make a measurement, the wave function collapses. It goes from a spread-out cloud of possibilities to a single, definite outcome. And there's no deeper reality underneath. You can't ask what the electron was doing before you measured it, because before you measured it, it wasn't doing anything definite. The measurement itself brings the outcome into being. Einstein found this deeply unsatisfying, not because he couldn't follow the math, he could follow it better than almost anyone, but because it offended his sense of what a physical theory should be. He believed there had to be an underlying reality, definite properties that particles actually have, whether you look at them or not. He spent years devising thought experiments to try to show that quantum mechanics was incomplete, that there had to be hidden variables, deeper information that the theory was missing, and at those Solvay conferences, he would present these thought experiments to Bohr, often over breakfast, and Bohr would go away, think furiously, and come back by dinner with a refutation. It became almost a ritual. Einstein would attack, Bohr would defend, and each time, quantum mechanics survived. One of the most famous of these thought experiments came later, in 1935, when Einstein, along with Boris Podolsky and Nathan Rosen, published a paper that introduced what's now called the EPR paradox. And this is worth slowing down for, because it touches on something that still feels genuinely strange, even today. Here's the setup. Imagine you have two particles that interact and then fly apart in opposite directions. Quantum mechanics says that certain properties of these particles can be correlated, entangled, to use the word Schrödinger coined, in such a way that measuring one particle instantly tells you something about the other, no matter how far apart they are. If you measure the spin of particle A and find it spinning up, you instantly know particle B is spinning down, even if particle B is on the other side of the galaxy. Einstein's argument was that this was absurd. Either the particles had definite properties all along, in which case quantum mechanics is incomplete because it doesn't describe those properties, or the measurement of one particle somehow instantly influences the other across any distance, which would violate the speed of light. He called this spooky action at a distance, and he meant it as a criticism. Surely, he argued, the simpler explanation is that the particles had definite spins from the moment they separated, like a pair of gloves. If you find the left glove in one box, you know the right glove is in the other box. No spookiness required. And for nearly 30 years, this seemed like a philosophical debate with no way to resolve it experimentally. Quantum mechanics kept making correct predictions, so most working physicists just used the math and didn't worry too much about what it meant. But then, in 1964, a physicist named John Bell, working at CERN in Geneva, figured out something remarkable. He showed that there was a measurable difference between Einstein's hidden variable idea and the predictions of standard quantum mechanics. He derived a set of inequalities, mathematical relationships, that any hidden variable theory would have to satisfy. And if quantum mechanics was right, those inequalities would be violated. Suddenly, the philosophical debate had become an experimental question. It took a while for the experiments to catch up. The technology wasn't easy. But starting in the 1970s and reaching a landmark result in 1982, the French physicist Alain Aspect and his team performed a series of increasingly sophisticated tests. They created pairs of entangled photons, sent them flying apart, and measured their properties with detectors that were switched randomly while the photons were already in flight. So there was no way for one photon to send a signal to the other about what was being measured. And the results were clear. Bell's inequalities were violated. The correlations were exactly what quantum mechanics predicted, and they were stronger than any hidden variable theory could account for. Einstein's intuition, beautiful as it was, turned out to be wrong on this point. Nature really is that strange. And here's what's wild. This doesn't actually let you send information faster than light. The correlations are real, but you can't use them to transmit a message because the individual measurement results on each side look completely random. It's only when you compare the two sets of results that you see the correlations. So relativity is safe. The speed limit holds. But the entanglement is real, and it's become one of the key resources in quantum computing and quantum cryptography today. When people talk about quantum computers being powerful, entanglement is a big part of why. It's not science fiction. It's engineering, being built right now, based on principles that Einstein called spooky. But let's pull back for a moment, because while all these foundational debates were happening in the first half of the 20th century, quantum mechanics was also doing something incredibly practical. It was explaining chemistry. Think about that. For all of human history, chemistry had been empirical. People knew that certain elements reacted with others, that atoms combined in specific ratios, that some materials conducted electricity and others didn't. But nobody really knew why. The periodic table, organized by Mendeleev in 1869, had this beautiful structure. Elements arranged in rows and columns, with similar properties repeating at regular intervals. But the reason for that structure was a mystery. Why do the noble gases not react with anything? Why do the alkali metals all behave similarly? Why does carbon form 4 bonds? Quantum mechanics answered all of it. Once you understand that electrons in atoms occupy specific energy levels, and that these levels have sublevels called orbitals with particular shapes and capacities, the entire periodic table falls into place. The first shell holds 2 electrons, the second holds 8, the third holds 18, though it fills in a particular order, and the chemical behavior of an element is determined almost entirely by how many electrons are in its outermost shell. Elements with full outer shells are stable. Those are your noble gases, helium, neon, argon, sitting contentedly in the rightmost column of the periodic table, barely reacting with anything. Elements with 1 electron in their outer shell, like sodium or potassium, are desperate to give it away, which is why they react so vigorously. Elements with 7 electrons in their outer shell, like chlorine or fluorine, are desperate to grab 1 more. Put sodium and chlorine together, and one hands off its electron to the other, and you get table salt. The whole drama of chemistry, every reaction, every material, every molecule in your body, comes down to electrons seeking stable configurations, and the rules governing those configurations come straight from quantum mechanics. And this is where something called the Pauli exclusion principle becomes essential. Wolfgang Pauli, an Austrian physicist with a legendarily sharp tongue, he once dismissed a colleague's paper by saying, "It's not even wrong," meaning it was so vague it couldn't even be tested. Proposed in 1925 that no 2 electrons in an atom can occupy exactly the same quantum state. Each electron needs its own unique set of quantum numbers. And this seemingly simple rule is the reason matter has structure at all. Without it, Every electron in an atom would collapse down to the lowest energy level. Atoms would be tiny and inert, and there would be no chemistry, no complexity, no you. The Pauli exclusion principle is why the periodic table has the shape it does, why atoms have the sizes they do, and ultimately, why solid matter is solid. When you push your hand against a table and it doesn't go through, a significant part of what's stopping it is the Pauli exclusion principle. Electrons in the atoms of your hand refusing to be squeezed into the same states as the electrons in the table. So by the late 1920s, the theoretical framework of quantum mechanics was largely in place. But there was a problem, and it was a big one. Quantum mechanics, as formulated by Schrödinger and Heisenberg, was not compatible with Einstein's special relativity. The Schrödinger equation works beautifully for electrons moving at modest speeds, but it doesn't account for the effects of special relativity, time dilation, length contraction, the equivalence of mass and energy. And electrons in heavy atoms, like gold or lead, move at a significant fraction of the speed of light. You need a theory that combines quantum mechanics with special relativity. And in 1928, a quiet, almost preternaturally brilliant British physicist named Paul Dirac found one. He wrote down an equation, the Dirac equation, that described the electron in a way that was fully consistent with both quantum mechanics and special relativity. And this equation did something nobody expected. It predicted the existence of something that shouldn't exist, or at least something that nobody had ever seen before. The Dirac equation, when you solved it, gave you two sets of solutions. One set described the electron perfectly, its spin, its magnetic properties, its behavior at relativistic speeds. All of that matched experiment beautifully. But the other set of solutions described a particle that was identical to the electron in every way except one. It had a positive charge, an anti-electron, a mirror image. Now, Dirac stared at these extra solutions and he didn't know what to do with them. This is 1928, remember? Nobody had ever detected a positively charged electron. The only positive particle anyone knew about was the proton, and protons are nearly 2,000 times heavier than electrons, clearly not the same thing. So Dirac initially tried to explain away these solutions. He proposed something called the Dirac sea. This idea that all of space was filled with an infinite ocean of negative energy electrons, and what we'd perceive as a positive electron was really just a hole in that sea, a place where a negative energy electron was missing. It was a strange, almost desperate idea, and even Dirac himself wasn't fully comfortable with it. He actually tried to argue at first that these holes might somehow be protons, which didn't work at all because the math clearly said the antiparticle had to have the same mass as the electron. But here's what's remarkable. Dirac trusted his equation. He trusted the mathematics even when it was telling him something that seemed physically absurd. And in 1931, he made the explicit prediction: there must exist a particle with the mass of an electron and a positive electric charge, an anti-electron. And then, in 1932, an American physicist named Carl Anderson was studying cosmic rays, these high-energy particles that rain down on Earth from space, using a cloud chamber. A cloud chamber is this beautiful, almost poetic piece of equipment. You fill a chamber with supersaturated vapor, and when a charged particle flies through it, it ionizes the gas molecules along its path, and those ions act as seeds for tiny droplets to condense on. So the particle literally leaves a visible trail, like a tiny contrail, and you can photograph it. Anderson had placed his cloud chamber in a strong magnetic field, which curves the paths of charged particles. Positive particles curve one way, negative particles curve the other, and how tightly they curve tells you their momentum. And in August of 1932, Anderson photographed a track that curved the wrong way. It curved like a positive particle, but it curved too tightly to be a proton. The particle was too light. It had the mass of an electron, but it was positive. He'd found it. Dirac's anti-electron. Anderson called it the positron, and that name stuck. Think about what just happened here. A mathematician wrote down an equation to describe something we already knew about, the electron, and the equation, purely through its own internal logic, predicted the existence of something entirely new, something no one had ever imagined. And then someone went and found it in the real world. If that doesn't give you a little chill, I don't know what will. This is one of those moments in the history of science where mathematics reaches out ahead of experiment and says, "There's something else out there. Go look." And it was right. The discovery of the positron opened up an entirely new idea. Antimatter. Every particle, it turns out, has an antiparticle. The electron has the positron. The proton has the antiproton, which wasn't discovered until 1955 at Berkeley. The neutron has the antineutron. When a particle meets its antiparticle, they annihilate each other. Both particles disappear and their entire mass is converted into energy, usually in the form of high-energy photons, gamma rays. Pure E equals mc squared in action. And the reverse can happen too. Enough energy concentrated in one place can spontaneously create a particle-antiparticle pair out of nothing, out of pure energy, matter and antimatter, conjured from light. And this leads to one of the deepest unsolved puzzles in all of physics, which is, why is there anything here at all? If the laws of physics treat matter and antimatter almost symmetrically, and they very nearly do, then the Big Bang should have produced equal amounts of both, and they should have annihilated each other completely, leaving a universe filled with nothing but radiation. No atoms, no stars, no planets, no you. But obviously that didn't happen. There's a tiny asymmetry somewhere, a slight preference for matter over antimatter, and nobody fully understands where it comes from. It's one of the great open questions, but we're getting ahead of ourselves. Let's come back to the 1930s, because the Dirac equation and the positron were really just the beginning of a much larger project, the development of quantum field theory. And this is where things get genuinely deep, so let's take it slow. Here's the basic idea. In ordinary quantum mechanics, the kind Schrödinger and Heisenberg built, you have particles, electrons for instance, and you describe them with wave functions. The particles are the fundamental objects, and the theory tells you how they behave. But in quantum field theory, the fundamental objects aren't particles at all. They're fields. Imagine a field as something that fills all of space, like a vast invisible fabric stretched out in every direction. There's an electron field that permeates the entire universe. There's a photon field. There's a quark field. And what we call a particle is really just a localized vibration, a little ripple in the corresponding field. An electron isn't a tiny ball sitting somewhere in space. It's an excitation of the electron field. A photon isn't a little pellet of light. It's a ripple in the electromagnetic field. Every electron in the universe is a vibration in the same field. That's why all electrons are identical. They're not separate objects that happen to look alike. They're all ripples in the same underlying thing. This is a genuinely profound shift in how you think about reality. Instead of a universe populated by billions of different particles flying around, you have a universe made of a handful of fields, and all the richness and complexity you see, every atom, every molecule, every star, is just those fields vibrating in different patterns. It's almost musical, if you think about it. Different notes played on the same set of strings. The first quantum field theory to be developed was quantum electrodynamics, or QED, which describes how electrons and photons interact. And the story of QED is one of the great intellectual dramas of 20th century physics, because for about 2 decades, it was a magnificent theory that kept giving nonsensical answers. The trouble was infinities. When physicists tried to use QED to calculate simple things, like the probability that 2 electrons would scatter off each other, or the precise energy levels of hydrogen, the calculations kept producing infinite results, not just big numbers. Infinity. Which is obviously wrong. You measure something in the lab and you get a perfectly finite number, but your theory says the answer should be infinite. Something was deeply broken. The problem had to do with what are called virtual particles. In quantum field theory, the vacuum, empty space, isn't really empty. The uncertainty principle, the same one Heisenberg discovered, means that energy can fluctuate briefly, and these fluctuations manifest as pairs of particles and antiparticles that pop into existence for an incredibly short time and then annihilate each other. They're called virtual particles because they exist for such a fleeting moment that you can't directly detect them, but they have real, measurable effects. And when you try to calculate those effects, you have to sum up contributions from virtual particles of every possible energy, all the way up to infinity. And those sums diverge. They blow up. Throughout the 1930s and into the 1940s, this problem plagued the best minds in physics. Dirac worked on it. Heisenberg worked on it. Pauli worked on it. Nobody could figure out how to get rid of the infinities. Some physicists began to wonder if quantum field theory was fundamentally wrong, if it needed to be replaced by something completely different. And then, in the late 1940s, 3 physicists independently figured out how to tame the infinities. Their names were Shinichiro Tomonaga in Japan, Julian Schwinger in the United States, and Richard Feynman, also in the United States. And they did it in 3 completely different ways that turned out to be mathematically equivalent, which is itself a remarkable echo of how Heisenberg and Schrödinger had done the same thing with quantum mechanics 2 decades earlier. The technique they developed is called renormalization, and it's one of those ideas that sounds like cheating but turns out to be deeply correct. Here's the rough idea. The infinities arise because you're calculating the properties of a bare electron, an electron with no cloud of virtual particles around it. But here's the thing. You can never observe a bare electron. Every real electron is always surrounded by a seething cloud of virtual particles that pop in and out of existence, and those virtual particles affect the electron's apparent mass and charge. What you actually measure in the lab is the dressed electron, the bare electron plus its cloud. So what renormalization does is essentially absorb the infinities into the definition of the electron's mass and charge. You say, I don't know what the bare mass is, and I don't care. I'll just use the measured mass as my starting point. And when you do that, all the infinities cancel out, and what's left are finite, calculable corrections. And those corrections are spectacularly accurate. QED predicts the magnetic moment of the electron, a quantity called the anomalous magnetic moment, or G-2, to more than 10 decimal places. And when you measure it in the lab, it agrees to more than 10 decimal places. This is the most precisely tested prediction in all of science. Nothing else even comes close. It's like predicting the distance from New York to Los Angeles to within the width of a human hair. QED works. Whatever philosophical discomfort you might have about the renormalization procedure, the results are undeniable. Now, Feynman deserves a moment here, because he's one of the most extraordinary characters in the history of physics, and his contribution to QED went beyond just solving the infinity problem. He invented an entirely new way of visualizing and calculating particle interactions, Feynman diagrams. These are simple little pictures where you draw lines representing particles and vertices where they interact. A straight line for an electron, a wavy line for a photon, and where they meet, that's an interaction. And each diagram corresponds to a precise mathematical expression. So instead of doing incredibly complicated integrals, you draw all the possible diagrams for a given process, write down the corresponding math, and add them up. It's a bookkeeping system of breathtaking elegance. Every physics student learns Feynman diagrams, and they're still the standard tool for calculating particle interactions today. Feynman himself was a character, a bongo-playing, safe-cracking, endlessly curious New Yorker who had worked on the Manhattan Project as a young man and went on to become one of the greatest teachers physics has ever known. He had this gift for cutting through formalism and getting to the physical heart of a problem. His lectures at Caltech in the early 1960s were legendary and were eventually published as the Feynman Lectures on Physics, which remain some of the best physics textbooks ever written. He also had a deep playfulness about him. He'd work on problems in strip clubs, pick locks for fun at Los Alamos, and once learned enough biology to make a genuine contribution to the field, just because he was curious. But underneath all the showmanship was a mind of extraordinary depth and precision. So by the early 1950s, QED was established as the gold standard of quantum field theories. It described the electromagnetic interaction, how charged particles interact through the exchange of photons, with breathtaking accuracy. But electromagnetism is only one of the fundamental forces of nature. There are others, and the question became, could you build similar quantum field theories for the other forces? Now, let's talk about those forces for a moment, because this is where the story starts to expand in a really beautiful way. By the mid-20th century, physicists recognized 4 fundamental forces in nature. You've got gravity, which holds planets in orbit and keeps your feet on the ground. You've got electromagnetism, which QED had conquered. And then you've got 2 forces that operate only at the scale of the atomic nucleus, forces you never directly experience in everyday life, but which are absolutely essential for the existence of matter. The strong nuclear force, which holds protons and neutrons together inside the nucleus. Remember, protons are all positively charged, so they repel each other electromagnetically, and you need something much stronger than electromagnetism to glue them together. And the weak nuclear force, which is responsible for certain types of radioactive decay, like beta decay, where a neutron transforms into a proton and emits an electron and a neutrino. The neutrino, actually, that's worth a quick detour. The neutrino was predicted in 1930 by Wolfgang Pauli, the same Pauli of the exclusion principle. He proposed it to solve a puzzle about beta decay. When a radioactive nucleus undergoes beta decay, it emits an electron, but the electron doesn't always come out with the same energy. Sometimes it's fast, sometimes it's slow. This seemed to violate conservation of energy. Where was the missing energy going? Pauli suggested, almost apologetically, that there must be a third particle being emitted along with the electron, a particle so light and so weakly interacting that it was escaping undetected, carrying away the missing energy. He called it the neutron at first, But when the actual neutron, the heavy neutral particle in the nucleus, was discovered by James Chadwick in 1932, the name was already taken. So Enrico Fermi, the great Italian physicist, gave Pauli's particle the diminutive Italian name, neutrino, the little neutral one. And Pauli himself famously said, "I have done a terrible thing. I have postulated a particle that cannot be detected." He was wrong about that. Neutrinos were finally detected in 1956 by Clyde Cowan and Frederick Rains. But he was right that they were extraordinarily difficult to catch. A neutrino can pass through a light year of solid lead and have only about a 50-50 chance of hitting anything. Right now, as you lie there, billions of neutrinos from the sun are passing through your body every second, and you feel absolutely nothing. But anyway, the point is that by the 1950s, physicists had these four forces and a beautiful theory for one of them. The challenge was to build equally successful theories for the strong and weak forces, and this is where the story takes a turn that would eventually lead to one of the most ambitious intellectual constructions in human history, what physicists call the Standard Model. And the path to get there was anything but straightforward. It involved a whole new zoo of particles that nobody asked for, a radical rethinking of what protons and neutrons actually are, and a mechanism for giving particles their mass that was so strange, so counterintuitive, that the physicist who first proposed it was largely ignored for years. Let's talk about all of that. So by the late 1950s, physicists had a problem that was almost embarrassing. They kept discovering new particles. Not one or two. Dozens. Every time they smashed protons into things at higher energies, or studied cosmic rays more carefully, or built a bigger accelerator, out popped another particle nobody had predicted. There were pions, kaons, lambda particles, sigma particles, psi particles, eta particles. The list kept growing. Enrico Fermi reportedly quipped, "If I could remember the names of all these particles, I'd be a botanist." And that captures the mood perfectly. Physics was supposed to be about simplicity, about finding the fundamental building blocks. Instead, it felt like they were cataloging butterflies. They called it the particle zoo. And for a while, it was genuinely confusing. Were all of these particles fundamental? Were they all on equal footing with the electron and the proton? That seemed unlikely. Nature doesn't usually work that way. When you find that many things that seem related, there's usually a deeper pattern underneath. Think about the periodic table of elements. In the 1860s, Mendeleev looked at the 60-odd elements known at the time and found a pattern. A repeating structure that organized them all and even predicted elements that hadn't been discovered yet. The periodic table was screaming that atoms weren't truly fundamental, that they had internal structure. And eventually, that's exactly what Thomson, Rutherford, and Bohr showed. So when physicists in the 1950s and 60s looked at this zoo of particles, the natural question was, is there a deeper layer? Are these particles made of something smaller? The answer came from a theoretical physicist named Murray Gell-Mann and independently from George Zweig, both working in the early 1960s. Gell-Mann had already done something remarkable in 1961. He'd found a way to organize the particle zoo into neat geometric patterns based on their properties, a classification scheme he called the Eightfold Way, a playful reference to Buddhist philosophy. It was like Mendeleev's periodic table for subatomic particles, and just like Mendeleev's table, it had gaps, places where a particle should exist but hadn't been found yet. In 1964, one of those predicted particles, called the omega-, was discovered at Brookhaven National Laboratory with exactly the properties Gell-Mann had predicted. That was a powerful moment. But Gell-Mann went further. He asked, what if the patterns in the eightfold way exist because all these particles, protons, neutrons, pions, kaons, all of them, are built from a smaller set of truly fundamental constituents? He proposed that there were 3 types of these constituents, and he gave them one of the most whimsical names in all of physics: quarks. He took the word from a line in James Joyce's Finnegan's Wake, 3 quarks for muster mark, which is such a perfectly odd choice for a fundamental building block of reality. Zweig, working independently at CERN, called them aces, but Gell-Mann's name stuck. Here's the idea. You take 3 types of quarks, Gell-Mann called them up, down, and strange, and you combine them according to specific rules, and you can build every single particle in the zoo. A proton? That's 2 up quarks and 1 down quark. A neutron? 2 down quarks and 1 up quark. The various strange particles that had been so puzzling? They contained 1 or more strange quarks, pions and kaons. Those were quark-antiquark pairs. The entire zoo, all those dozens of seemingly random particles, could be constructed from just 3 building blocks and their antimatter counterparts. That's the kind of simplification that makes a physicist's heart sing. But here's what's really wild about quarks. Nobody could find one by itself. You could smash protons apart as hard as you wanted, and you'd never see a lone quark come flying out. This was deeply strange. Every other particle could be isolated. You could catch an electron, trap a proton, detect a neutrino if you were patient enough, but quarks seem to be permanently confined inside larger particles. This property is actually called confinement, and it's one of the most remarkable features of the strong nuclear force. The force between quarks doesn't weaken as they get farther apart. It actually gets stronger, like stretching a rubber band. If you pull 2 quarks apart with enough energy, instead of separating them, the energy in the stretched force field between them creates a new quark-antiquark pair. You end up with more particles, but still no free quarks. It's as if you tried to isolate the north pole of a magnet by cutting it in half, and instead of getting a north piece and a south piece, you got 2 complete magnets, each with its own north and south. For years, many physicists thought quarks might just be a mathematical trick, a bookkeeping device that organized the patterns, but didn't correspond to real physical entities. But experiments at the Stanford Linear Accelerator Center in the late 1960s, led by Jerome Friedman, Henry Kendall, and Richard Taylor, changed that. They fired high-energy electrons at protons and watched how the electrons scattered. If a proton were a smooth, uniform blob, the electrons would scatter gently. But that's not what happened. The electrons scattered sharply, at large angles, as if they were bouncing off small, hard objects inside the proton. It was Rutherford's gold foil experiment all over again, but 1 level deeper. Just as Rutherford had discovered the nucleus inside the atom, these experiments revealed point-like structures inside the proton. They were real. Quarks were real. Now, the force that holds quarks together, the strong nuclear force, needed its own quantum field theory, just as electromagnetism had QED. That theory is called quantum chromodynamics, or QCD, and the name gives you a hint about how it works. In QED, the electromagnetic force arises because charged particles exchange photons. In QCD, quarks carry a different kind of charge, whimsically called color charge. Not actual color, of course, but a property that comes in 3 types, which physicists labeled red, green, and blue. And just as photons are the force carriers in QED, the strong force has its own carriers, particles called gluons. But here's where QCD gets much more complicated than QED. Photons don't carry electric charge themselves. They're electrically neutral, so they don't interact with each other. Gluons, on the other hand, carry color charge. They interact with each other. This self-interaction is what makes the strong force so different from electromagnetism. It's what leads to confinement, to that rubber band-like behavior. It makes the mathematics ferociously difficult. QCD is, in many ways, a much harder theory to work with than QED. Meanwhile, the weak nuclear force, the one responsible for beta decay, the one that Pauli's neutrinos were entangled with, was getting its own theoretical treatment. And this is where things get really beautiful, because in the 1960s and 70s, physicists realized that the weak force and electromagnetism, which seem so different on the surface, are actually two aspects of a single unified force. This unification was worked out by Sheldon Glashow, Abdus Salam, and Steven Weinberg, working somewhat independently over the course of several years. The idea is that at very high energies, the kind of energies that existed in the first moments after the Big Bang, there's no distinction between the electromagnetic force and the weak force. They're one thing, called the electroweak force. But as the universe cooled, a symmetry broke, and the single force split into the two different forces we observe today. It's a bit like how water looks the same in every direction when it's liquid, but when it freezes into ice, the crystal structure picks out specific directions. The underlying symmetry is still there, but it's hidden. And this is where that mysterious mass-giving mechanism comes in, the one I started to mention. Because there was a serious problem with the electroweak theory. The mathematics worked beautifully, but only if the force-carrying particles of the weak force, called the W and Z bosons, were massless, like the photon. But if they were massless, the weak force would be long-range, like electromagnetism. And it's not. The weak force is incredibly short-range. It only operates across distances smaller than an atomic nucleus. For the weak force to be short-range, its carrier particles had to be massive. Very massive, in fact, about 80 to 90 times the mass of a proton. But if you just stuck mass into the equations by hand, the whole theory fell apart. The mathematics produced infinities that couldn't be tamed by renormalization. The solution came from a mechanism proposed in 1964 by several groups of physicists, but most prominently associated with Peter Higgs, a quiet, unassuming theorist at the University of Edinburgh. The idea, also developed independently by Robert Brout and François Englert in Brussels, and by Gerald Guralnick, Carl Hagen, and Tom Kibble in London, was that there exists a field permeating all of space, and particles acquire mass through their interaction with this field. Think of it this way. Imagine a room full of people at a party, evenly spread out. If a nobody walks through, they pass through easily. That's like a massless particle. But if a celebrity walks in, people cluster around them, slowing them down, making it harder for them to accelerate. That resistance to acceleration is what we experience as mass. The Higgs field works something like that. Particles that interact strongly with it are heavy. Particles that interact weakly with it are light, and photons don't interact with it at all, which is why they're massless and travel at the speed of light. Now, here's the thing about the Higgs mechanism. When Higgs submitted his paper in 1964, it was initially rejected. The journal sent it back. He revised it, added a crucial paragraph, pointing out that the theory predicted a new particle, a quantum of the Higgs field, what we now call the Higgs boson, and it was published. But for years, decades even, it was a theoretical idea without direct experimental confirmation. The Higgs boson was predicted to exist, but nobody had ever seen one. Finding it required collisions at energies that were beyond the reach of any accelerator available at the time. That search would take nearly half a century. it became one of the great quests of modern physics, building machines of almost inconceivable scale and precision, pushing technology to its absolute limits, all to find a single particle that would confirm or deny the mechanism by which everything in the universe has mass. And the machine that finally did it, the Large Hadron Collider at CERN, straddling the border between Switzerland and France, is itself one of the most extraordinary engineering achievements in human history. A ring of superconducting magnets 27 kilometers in circumference, cooled to temperatures colder than outer space, accelerating protons to 99.9999991% of the speed of light. On July 4, 2012, two independent detector teams at the LHC, ATLAS and CMS, each involving thousands of physicists, announced that they had found it, the Higgs boson. Peter Higgs, then 83 years old, was in the audience. He wept. So by 2012, the Standard Model was essentially complete. And what a construction it is. 3 generations of quarks, up and down, charm and strange, top and bottom. 3 generations of leptons, the electron and its neutrino, the muon and its neutrino, the tau and its neutrino, force carriers, photons for electromagnetism, W and Z bosons for the weak force, 8 types of gluons for the strong force, and the Higgs boson, the quantum of the field that gives particles their mass. That's it. That's the inventory of fundamental particles, as far as we know. Everything you've ever seen, touched, tasted, or felt, every star, every planet, every cell in your body, is built from these pieces, interacting through these forces. And the precision of this theory is almost absurd. Remember how QED could predict the electron's magnetic moment to 10 decimal places. The Standard Model as a whole has been tested in thousands of experiments over decades, and it has passed every single one. It is, by any reasonable measure, the most successful scientific theory ever constructed. But, and you probably felt this coming, it's not complete. It can't be. Because the Standard Model, for all its triumphs, leaves some enormous questions unanswered. And perhaps the most glaring omission is the one force it doesn't include at all, the one force that you feel most directly every moment of your life. Gravity. The Standard Model has nothing to say about gravity, and the story of why gravity is so stubbornly resistant to being folded into the quantum framework, why it refuses to play by the same rules as the other 3 forces, that's a story that takes us all the way back to Einstein, and then forward into some of the strangest and most speculative ideas in all of physics. So let's go there. Gravity. It's the first force any of us ever experiences. Before you can walk, before you can even lift your head, gravity is there, pulling you into the crib, holding you against the earth. It's so constant, so omnipresent, that we barely notice it. Like the hum of a refrigerator, you only hear when it stops. And yet, of the 4 fundamental forces, gravity is by far the most mysterious. Not because we don't understand how it behaves, we do beautifully, but because we don't understand how it fits with everything else. Let's go back to Einstein for a moment. We talked about him earlier, back when we were exploring how quantum mechanics got started. Einstein was one of its founders, remember? His 1905 paper on the photoelectric effect, showing that light comes in packets of energy, was one of the key sparks that lit the quantum revolution. But Einstein spent the second half of his career working on something very different. He was working on gravity. And the theory he produced, general relativity, completed in 1915, is one of the most beautiful intellectual achievements in human history. Here's what Einstein realized. Gravity isn't really a force in the way Newton described it. Newton said that masses attract each other across empty space, instantaneously, through some invisible pull. And that works. It works incredibly well for calculating orbits and trajectories and tides, but Newton himself admitted he had no idea how it actually worked. He called it action at a distance, and said he wouldn't feign hypotheses about its mechanism. Einstein figured out the mechanism, and it's stunning. Mass and energy, Einstein showed, actually bend the fabric of space-time itself. Imagine a heavy bowling ball sitting on a stretched rubber sheet. The sheet curves around the ball, and if you roll a marble nearby, it doesn't travel in a straight line anymore. It curves toward the bowling ball, not because the bowling ball is pulling it, but because the sheet itself is warped. That's gravity, according to Einstein. The Earth isn't pulling you down. The Earth's mass is curving the space-time around it, and you're following the most natural path through that curved geometry. What you feel as the force of gravity is actually the floor pushing up against you, preventing you from following your natural free-fall path through curved space-time. Now, that's a gorgeous idea. And it's not just philosophically elegant, it makes specific, testable predictions that differ from Newton's theory. It predicted that light itself would bend around massive objects, which was confirmed during a solar eclipse in 1919 by Arthur Eddington's expedition, making Einstein world-famous overnight. It predicted that time runs slower in stronger gravitational fields, which has been confirmed with atomic clocks. GPS satellites have to correct for this effect, or your phone's navigation would drift by kilometers per day. It predicted gravitational waves, ripples in space-time itself, which were finally detected directly by LIGO in September 2015, 100 years after Einstein wrote down the equations. General relativity has been tested again and again in increasingly extreme conditions, and it has never failed. So, here's the puzzle. You've got two theories: quantum mechanics and its offspring, quantum field theory, which describes 3 of the 4 forces with breathtaking precision, and general relativity, which describes gravity with equal precision. Both are spectacularly successful. Both have been confirmed by experiment beyond any reasonable doubt, and they are, at a fundamental level, incompatible with each other. Think about what that means. We have 2 descriptions of reality that both work, but they can't both be the final word because they describe the universe in fundamentally different ways. Quantum field theory says forces are carried by particles, photons, gluons, W and Z bosons, exchanged between other particles in a background of flat spacetime. General relativity says gravity isn't carried by particles at all. It's the curvature of spacetime itself, and spacetime is dynamic, flexible, responsive to the matter and energy within it. In one theory, spacetime is the stage. In the other, spacetime is one of the actors. For most practical purposes, this doesn't matter. Gravity is so absurdly weak compared to the other forces. And yes, I know that sounds strange, given how inescapable it feels. But think about it. A tiny refrigerator magnet can hold a paperclip against the gravitational pull of the entire Earth. That in the realm of subatomic particles, where quantum effects dominate, gravity is negligible. And in the realm of planets and stars and galaxies, where gravity dominates, quantum effects are negligible. The 2 theories govern different domains, and they rarely need to talk to each other. But there are places where they collide. Places where you have enormous mass crammed into incredibly tiny spaces, so that both quantum effects and gravitational effects are simultaneously important. The interior of a black hole, for instance, where general relativity predicts that matter collapses to an infinitely dense point, a singularity. Infinity is not a physical answer. It's a sign that your theory has broken down, that you've pushed it beyond its domain of validity, or the very first instant of the Big Bang, when the entire observable universe was compressed into a region smaller than an atom. To describe what happened there, you need a theory that is both quantum mechanical and gravitational. You need quantum gravity, and we don't have one. Not a complete, experimentally verified one. Not yet. It's not for lack of trying. Physicists have been working on this problem since at least the 1930s. The most natural approach, the one that worked so brilliantly for electromagnetism and the strong and weak forces, would be to quantize gravity the same way. Treat space-time curvature as a field, find its quantum excitations, call them gravitons, and build a quantum field theory of gravity. People tried this, and what they found was that the theory is non-renormalizable. Remember renormalization, that mathematical trick that Tominaga, Schwinger, and Feynman used to tame the infinities in QED? When you try the same approach with gravity, the infinities multiply faster than you can absorb them. Every time you try to fix one, more appear. The procedure that worked so elegantly for the other forces simply fails for gravity. The theory produces nonsensical predictions at high energies, and no amount of clever mathematical maneuvering can fix it. This is deeply frustrating, and it's been the central open problem in theoretical physics for decades. But it's also led to some of the most creative and ambitious ideas in the history of science. The most famous attempt is string theory. The basic idea emerged in the late 1960s and early 1970s, originally in a completely different context. People were trying to understand the strong nuclear force before QCD came along. In 1968, a young Italian physicist named Gabriele Veneziano was looking at data from particle collisions and noticed that a particular mathematical function, the Euler beta function, seemed to describe the patterns he was seeing. It was a remarkable observation, but nobody understood why it worked. Then, in 1970, Yoichiro Nambu, Holger Besch-Nielsen, and Leonard Susskind independently realized what the mathematics was describing: tiny, vibrating strings. Not point particles, one-dimensional strings, unimaginably small, vibrating at different frequencies. Here's the beautiful part. A violin string can vibrate in different modes, its fundamental frequency, its harmonics, and each mode produces a different note. These theoretical strings do the same thing. Each vibrational mode corresponds to a different particle. One mode gives you a photon, another gives you an electron, another gives you a quark. All the different particles in nature might be, at the most fundamental level, the same thing. A single type of string, vibrating in different ways. That's an extraordinarily unifying idea. But here's what really got people excited. When physicists worked out the mathematics of these vibrating strings, they found that one of the vibrational modes automatically, unavoidably, produces a massless particle with spin 2. And a massless spin 2 particle is exactly what a graviton would be, the hypothetical quantum carrier of gravity. String theory doesn't just accommodate gravity, it demands it. Gravity falls out of the mathematics whether you want it or not. That was electrifying. For the first time, there was a framework that seemed to naturally unify quantum mechanics and gravity. But string theory comes with some very unusual baggage. For the mathematics to be consistent, the strings can't vibrate in just 3 spatial dimensions. They need more room. The original version of string theory, called bosonic string theory, required 26 dimensions. Later versions, incorporating something called supersymmetry, a proposed symmetry between the 2 broad classes of particles, fermions and bosons, brought that down to 10 dimensions. 10. We experience 3 dimensions of space and 1 of time. Where are the other 6? The standard answer is that they're compactified, curled up so small that we can't detect them. Imagine an ant walking on a garden hose. From far away, the hose looks like a one-dimensional line, but up close, the ant can walk around the circular cross-section. There's an extra dimension that's too small to see from a distance. String theory proposes that at every point in the space you move through, there are 6 additional tiny dimensions, curled up into complex geometric shapes called Calabi-Yau manifolds. The specific shape of these extra dimensions would determine the properties of the particles we observe, their masses, their charges, their interactions. It's a breathtaking idea. It's also, as of right now, completely unverified by experiment. The strings, if they exist, would be on the order of the Planck length, about 10 to the minus 35 meters. That's so small that to probe it directly, you'd need a particle accelerator roughly the size of the Milky Way galaxy. We can't build that. So string theory remains, for now, a mathematical framework of extraordinary richness and beauty that may or may not describe our universe. And string theory isn't the only approach. There's another major program called loop quantum gravity, pioneered by Abhay Ashtekar, Carlo Rovelli, Lee Smolin, and others starting in the 1980s. Loop quantum gravity takes a very different philosophical stance. Instead of adding new ingredients like strings and extra dimensions, it tries to quantize gravity directly, to apply quantum principles to Einstein's general relativity itself, but in a cleverer way than the naive approach that led to non-renormalizability. The result is a picture where space-time itself is quantized. Space isn't smooth and continuous, it's made of discrete chunks, tiny granular units of volume and area, woven together in a network called a spin foam. At the Planck scale, space would look something like a fabric made of interlocking loops, hence the name. In loop quantum gravity, there's no need for extra dimensions. There's no need for strings. There's no need for supersymmetry. It's a leaner, more conservative approach in some ways, but it has its own challenges. It's been difficult to show that the theory reproduces general relativity in the large-scale limit. That is, that this granular quantum spacetime, when you zoom out, looks like the smooth curved spacetime Einstein described. And like string theory, it has yet to produce a prediction that's been confirmed by experiment. So here we are, 2 magnificent but incomplete attempts to solve the deepest puzzle in physics. And there are others, causal set theory, which proposes that spacetime is fundamentally a discrete set of points with causal relationships between them. Asymptotic safety, which suggests that gravity might actually be renormalizable after all if you look at it the right way, and various approaches involving emergent spacetime, where space and time themselves aren't fundamental but arise from something deeper, perhaps quantum entanglement. That last idea, that spacetime might emerge from entanglement, is one of the most exciting developments of recent years. It connects to work by Juan Maldacena, who in 1997 proposed something called the ADS/CFT correspondence, which suggests a deep mathematical equivalence between a theory of gravity in a certain kind of curved spacetime and a quantum field theory without gravity living on the boundary of that spacetime. It's sometimes called the holographic principle, the idea that all the information about a volume of space can be encoded on its boundary, like a hologram. This has become one of the most active areas of theoretical physics, blurring the lines between quantum information theory, gravity, and even condensed matter physics. But notice something. All of these ideas, string theory, loop quantum gravity, holography, emergent spacetime, they're all, at this point, theoretical frameworks. They're mathematically sophisticated, deeply studied, and genuinely illuminating. But none of them has been confirmed by experiment. None of them has made a prediction that we've gone out and verified the way Dirac's equation predicted antimatter, or the way Gell-Mann's eightfold way predicted the omega-minus baryon, or the way the Standard Model predicted the Higgs boson. And that's not because the physicists working on them aren't brilliant. They are, staggeringly so. It's because the phenomena these theories describe occur at energy scales and length scales so extreme that our current technology simply can't reach them. And this raises a question that's as much philosophical as it is scientific. A question about the nature of physics itself, about what counts as knowledge, about what we can reasonably hope to understand about a universe that may keep some of its deepest secrets locked behind barriers of scale that no conceivable experiment could ever breach. It's a question that would have fascinated Einstein, who spent his last decade searching for a unified theory and never found one. It's a question that haunts the most ambitious physicists alive today, and it connects to something even broader, to the realization that the Standard Model, for all its glory, accounts for only about 5% of the universe's total mass and energy content. Only about 5%, which means that everything we've talked about tonight, every quark, every lepton, every force carrier, every atom in every star in every galaxy you've ever seen in a photograph, all of it, all of that magnificent architecture of matter and force, is just a thin, bright film floating on top of something vastly larger and almost entirely mysterious. So let's talk about what the other 95% might be, because this is where physics stands right now, at the edge of what it knows, squinting into a darkness that is, quite literally, dark. The story starts, as so many good ones do, with someone noticing that the numbers don't add up. In the 1930s, a Swiss astronomer named Fritz Zwicky was studying galaxy clusters, big gravitationally bound collections of galaxies, hundreds or even thousands of them orbiting around a common center of mass. Zwicky was looking at the Coma cluster, about 300 million light-years away, and he did something straightforward. He measured how fast the individual galaxies in the cluster were moving, and he used that to estimate how much total mass the cluster needed to have in order to keep those galaxies from flying apart. It's the same basic logic you'd use if you watched a ball on a string being swung in a circle. The faster it goes, the stronger the string has to be, which in gravitational terms means the more mass there has to be at the center pulling it inward. Zwicky did the calculation and found that the galaxies were moving way too fast. Based on the visible matter he could see, the stars, the glowing gas, the cluster didn't have nearly enough mass to hold itself together. The galaxies should have been flying off into space. But they weren't. Something invisible was providing the extra gravitational pull. Zwicky called it Dunkel Materie, dark matter. Now Zwicky was a brilliant and famously difficult man. He called his colleagues spherical bastards, because he said they were bastards no matter which way you looked at them. He was not well liked, and his dark matter idea was largely ignored for decades. People thought maybe he'd made an error, maybe his measurements were off, maybe there was some simpler explanation. But then, in the 1970s, an American astronomer named Vera Rubin found the same problem in a completely different context, and she found it so clearly and so repeatedly that it became impossible to ignore. Rubin was studying the rotation curves of individual spiral galaxies, how fast stars orbit around the center of a galaxy as a function of their distance from that center. And here's what you'd expect. In our solar system, planets close to the sun orbit fast, and planets far from the sun orbit slowly. Mercury zips around, Neptune crawls. That's because most of the mass is concentrated in the sun, So the farther out you go, the weaker the gravitational pull, and the slower you need to move to stay in orbit. You'd expect the same thing in a galaxy. Stars near the bright central bulge should orbit fast, and stars out in the dim outskirts should orbit much more slowly, because most of the visible mass is concentrated in the center. But that's not what Rubin found. Working with Kent Ford, who had built an extremely sensitive spectrograph, she measured the rotation speeds of stars in galaxy after galaxy, and the result was always the same. Stars in the outer regions of galaxies were moving just as fast as stars near the center. The rotation curves were flat. They didn't drop off the way Newtonian gravity predicted they should if the only mass present was the visible matter. It was as if every galaxy was embedded in a vast, invisible halo of additional mass that didn't emit light, didn't absorb light, didn't interact with light at all, but exerted gravitational pull just the same. This was Zwicky's dark matter again, but now seen galaxy by galaxy, measured with precision, confirmed over and over. And Rubin, who faced significant obstacles as a woman in astronomy in the 1960s and 70s. She'd been discouraged from pursuing graduate work, been told she couldn't use certain telescopes because they didn't have women's restrooms. Rubin quietly and methodically built a case so strong that the physics community had to take it seriously. And then more evidence piled on. Gravitational lensing, the bending of light from distant galaxies by the gravity of intervening mass, an effect predicted by general relativity, showed that galaxy clusters contained far more mass than their visible matter could account for. The cosmic microwave background, that ancient light from when the universe was only about 380,000 years old, showed patterns in its temperature fluctuations that only made sense if dark matter was present in the early universe, providing gravitational scaffolding for ordinary matter to clump around and eventually form galaxies. Computer simulations of cosmic structure formation, how the universe went from a nearly uniform hot soup to the vast web of galaxies and voids we see today, only produced results matching observations when dark matter was included. Take it out, and the simulated universe looks nothing like the real one. So what is dark matter? Here's the honest answer. We don't know. We know it has mass. We know it interacts gravitationally. We know it doesn't interact with the electromagnetic force, which means it doesn't emit, absorb, or reflect light. That's why it's dark. It appears not to interact via the strong nuclear force either. It might interact through the weak force, or it might interact through some force we haven't discovered yet, or it might interact with ordinary matter only through gravity and nothing else. The leading candidates for dark matter particles have names like WIMPs, weakly interacting massive particles, and axions, a much lighter hypothetical particle originally proposed to solve a different problem in QCD. There are underground detectors right now, deep in mines in Italy and South Dakota and Canada, shielded from cosmic rays by kilometers of rock, waiting patiently for a dark matter particle to bump into an ordinary atom and produce a tiny, telltale signal. So far, nothing definitive. The search continues. And then there's the other piece of that 95%. And honestly, this one is even stranger. In 1998, two teams of astronomers, the Supernova Cosmology Project, led by Saul Perlmutter, and the High Z Supernova Search Team, led by Brian Schmidt and Adam Rees, were both trying to measure how fast the expansion of the universe was slowing down. Because that's what everyone expected. The universe has been expanding since the Big Bang. We've known that since Hubble's observations in the 1920s. But gravity should be gradually pulling everything back, decelerating the expansion like a ball thrown upward that slows as it rises. The question was just how much the expansion was decelerating, and measuring that would tell you about the ultimate fate of the universe. Would it expand forever, or eventually collapse back on itself? Both teams were using Type 1a supernovae as distance markers. These are a particular kind of stellar explosion that, because of the physics involved, always reaches roughly the same peak brightness. So if you see one and it looks dim, you know it's far away, and if it looks bright, it's closer. They're sometimes called standard candles. You know how bright the candle actually is, so you can figure out how far away it must be based on how bright it appears. By measuring both the distance to these supernovae and the redshift of their host galaxies, which tells you how fast those galaxies are receding, you can map out the expansion history of the universe. And what both teams found, independently, was shocking. The distant supernovae were dimmer than expected. Not brighter, dimmer. Which meant they were farther away than they should have been if the expansion were slowing down. The expansion of the universe wasn't decelerating at all. It was accelerating. The universe is flying apart faster and faster, and some unknown energy permeating all of space, is pushing it. This something was given the name dark energy, and it makes up roughly 68% of the total energy content of the universe. Dark matter accounts for about 27%, and everything else, every star, every planet, every atom, every particle the Standard Model describes, that's the remaining 5%. Think about that for a second. The most successful theory in the history of physics, the Standard Model, describes 5% of what the universe is made of. We are, in a very real sense, profoundly ignorant about the cosmos we inhabit. Now, dark energy is even more mysterious than dark matter. With dark matter, we at least have a clear picture of what it does. It clumps, it gravitates, it forms halos around galaxies. We just don't know what particle it is. With dark energy, we're not even sure about the basic framework. The simplest explanation is that dark energy is the cosmological constant, a constant energy density filling all of space uniformly. Einstein actually introduced a cosmological constant into his equations of general relativity back in 1917, for different reasons. He was trying to make the universe static, which we now know it isn't, and he later called it his biggest blunder. But it turns out something very like it might be real, just with a different value and a different interpretation. In quantum field theory, empty space isn't truly empty. It's seething with virtual particle-antiparticle pairs popping in and out of existence, and this vacuum energy should contribute a constant energy density to space. The problem is that when you actually calculate how much vacuum energy quantum field theory predicts, you get a number that's roughly 10 to the 120th power times larger than the observed value of dark energy. That's not a small discrepancy. That is, by some measures, the worst prediction in the history of physics. It's sometimes called the cosmological constant problem, and it remains one of the deepest unsolved puzzles in all of science. So here we are. The Standard Model is complete in the sense that the Higgs boson has been found and every particle it predicts has been observed, but it's incomplete in almost every other sense. It doesn't include gravity. It doesn't explain dark matter. It doesn't explain dark energy. It doesn't explain why there's more matter than antimatter in the universe. Remember, Dirac's equation predicted that matter and antimatter should be created in equal amounts. So where did all the antimatter go? It doesn't explain why neutrinos have mass. The original Standard Model assumed they were massless, but experiments in the late 1990s showed that they oscillate between flavors, which is only possible if they have mass. It has about 19 free parameters, numbers like particle masses and coupling constants that have to be measured experimentally and plugged in by hand, with no deeper explanation for why they have the values they do. And some of those values are suspiciously fine-tuned. The Higgs boson mass, for instance, is about 125 giga-electronvolts, which is remarkably light, given that quantum corrections should push it up to something close to the Planck scale. This is called the hierarchy problem, and it was one of the main motivations for supersymmetry. The idea that every particle has a heavier partner whose quantum contributions would cancel out the problematic corrections. But the Large Hadron Collider has searched extensively for supersymmetric particles and found none, at least not at the energies accessible so far. That doesn't rule supersymmetry out entirely, but it's pushed it into a corner, and some physicists have started to wonder whether the fine-tuning might just be a brute fact about our universe, or whether it might be explained by something else entirely, perhaps the anthropic principle, perhaps the multiverse, perhaps something nobody has thought of yet. And this is where physics finds itself tonight, as you lie here listening. At a genuinely extraordinary moment. The tools are more powerful than they've ever been. Particle colliders, gravitational-wave detectors, space telescopes mapping the cosmic microwave background with exquisite precision, neutrino observatories buried in Antarctic ice, dark matter detectors waiting in silence underground. The theoretical frameworks are rich and deep and mathematically beautiful. But the biggest questions remain open. What is dark matter? What is dark energy? How do you reconcile quantum mechanics with gravity? Why does the universe have the particular parameters it has? Is there a deeper theory beneath the standard model, the way the standard model turned out to be deeper than the particle zoo that preceded it? You know, there's something comforting about the fact that we don't have all the answers. It means the story isn't over. Every theory we've talked about tonight, from Democritus's atoms to Newton's gravity to Maxwell's fields, to Einstein's space-time, to the wild quantum world of Bohr and Heisenberg and Dirac and Feynman, to the quarks and gluons and the Higgs field, every single one of them was once the frontier. Once, the place where the smartest people alive were squinting into the unknown and saying, "I think I see something, but I'm not sure what it is yet." And then someone figured out the next piece, and the picture got a little clearer, and new questions opened up that nobody had even thought to ask before. That's what physics is, really. Not a collection of facts, but a process. A conversation between human curiosity and the universe's willingness to answer, sometimes clearly, sometimes in riddles, sometimes in a whisper so faint you need a detector the size of a small city to hear it. And right now, someone is working on the next piece. Somewhere, probably in a cluttered office at 2 a.m, someone is staring at an equation that doesn't quite work, or a data set that doesn't quite fit, and they're about to have an idea. Maybe it'll be wrong. Most ideas are. But maybe, just maybe, it'll be the thread that, when pulled, unravels something beautiful. That's a good thought to fall asleep to, I think. The universe is vast and strange, and mostly made of things we can't see or name. But we've figured out so much already, starting from almost nothing, starting from people looking up at the sky and wondering. And the figuring out continues, quietly, patiently, while you rest. The stars are still burning. The galaxies are still turning. The dark matter is still holding everything together, whatever it is. And somewhere, someone is still asking the next question. So let that carry you off. Let the weight of all these ideas settle like a blanket. Quarks and leptons and gauge bosons and curved spacetime and vibrating strings and spin foams and the slow, accelerating expansion of everything into everything else. You don't need to hold on to any of it. It'll all be here in the morning. The universe is patient. It's been working on these puzzles for 13.8 billion years. It can wait while you sleep,